at this point, we have our weighted integral, and we have the assumed shapes for the temperature and the weighting function. And our weighting function is arbitrary, but we have reduced the arbitrariness of the weighting function to the arbitrariness of the values at the nodes. So we want to satisfy this for an arbitrary weighting function of this shape. How do we do that? What we do is we do an integration by parts. So if you have forgotten your integration by parts, you might want to quickly look it up on the internet, and then this might make more sense. So here I've written out what you will get from the integration by parts, and let me unpack that. So this is the term. So the weighting function multiplied by this is the term that you would do the integration by parts on. So first you will get, you will integrate that, so you'll get dt dx, and then you'll evaluate, this product of this and the integral of that at the boundaries. So there's no integral happening in the first term, it's just an evaluation of the boundaries. And then you get a second term where you take your first function and you differentiate that. That's just the constant. And you integrate your second function. And when you integrate d squared t dx squared, you will get dt dx and dx. So now key things happened, okay? Here I have, in the original differential equation, I have a second derivative for the temperature. But here I have the first derivative. And I know that the second derivative doesn't behave very well, right? So second derivative is 0 everywhere, and it's not defined at the nodes. Whereas the first derivative is defined. It's discontinuous at the nodes. That's not a big problem when you're doing integration. Which means that now I can use this shape in here, but I can't use this shape in my original differential equation. Which means that this has, this form has fewer restrictions on the shape you assume. For that matter, for that reason, this is called the weak form. And the original differential equation is called the strong form. And the key thing is, because you've reduced the order of the derivative by 1. And then you get, that term is just from here. And you don't do any integration by parts over there. And that's equal to 0. And next what we need to do is take these shapes and plug it into this and get our algebraic equations. So that's what we will look at next.